Hello there and welcome to the Deep Sleep Discoveries channel. Tonight we drift into the ancient and extraordinary world beneath our feet, the deep memory of our planet written in stone. Long before cities rose or oceans had names, the Earth was already alive, reshaping itself in silence. Mountains climbed towards stars, seas vanished and returned, continents wandered across glowing rivers of rock. The ground beneath you is ancient beyond imagination, and yet it is still moving, still breathing, still changing. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe. Let your eyes grow heavy, and let the ancient earth cradle your thoughts. Let's begin. If you could shrink the planet to the size of an apple, the crust, the solid outer shell we live on, would be no thicker than that fruit's skin. This idea feels almost impossible, yet it is true. The continents and ocean floors together form a layer that on average extends only about 30 kilometers deep beneath land and less than 10 beneath the sea. Everything we know, every forest, city, and ocean exists atop a layer so thin it could almost disappear in scale. Beneath that delicate shell lies something far more substantial. The mantle stretches downward into depths we can scarcely imagine, making up the vast majority of everything solid within our world. This thin crust floats upon that deeper realm like the most fragile of rafts. Beneath the thin crust lies the mantle, a vast region of rock that makes up most of Earth's volume and mass. Stretching nearly 3,000 kilometers deep, it contains more matter than all the oceans, continents, and atmosphere combined. The mantle is not molten, as many imagine, but solid rock so hot it flows like an incredibly thick liquid over millions of years. This slow churning drives the movement of continents above, carrying them across the planet's surface in an endless dance. The mantle's composition is rich in silicate minerals, iron and magnesium, giving it properties unlike anything we encounter at the surface. Its patient circulation shapes everything from volcanic eruptions to the paths of drifting land masses. Deep within this realm, pressures become so immense that minerals transform into forms that cannot exist anywhere else. And deeper still, at the mantle's heart, lies something even more extraordinary. At the very center of the planet, buried beneath thousands of kilometers of rock and molten metal, lies a solid sphere of iron and nickel. This inner core, though subjected to temperatures that would melt any surface material, remains frozen solid due to the crushing pressure of everything above it. It measures about 1,200 kilometers across, roughly 3/4 the size of the Moon. The atoms within it are packed so tightly they cannot move freely enough to become liquid. This hidden sphere spins slightly faster than the rest of the planet, completing an extra rotation every few centuries. Scientists discovered its existence not by drilling, but by studying how earthquake waves behave as they pass through the planet's depths. Some waves disappear entirely, while others bend and slow, revealing the layers within. Surrounding this solid heart is an ocean of liquid metal that never rests. Wrapped around the solid inner core flows a sea of molten iron and nickel, 2,000 kilometers thick and heated to temperatures rivaling the surface of the sun. This liquid outer core churns in vast convection currents, driven by heat escaping from the planet's formation and the decay of radioactive elements deep within. As the molten metal flows, it generates electric currents that produce Earth's magnetic field, the invisible shield that protects all life from harmful solar radiation. This process, called the geodynamo, has operated for billions of years, though the field's strength and direction have changed countless times. Without this flowing metal ocean, compasses would not point north, and the atmosphere might have been stripped away by solar winds long ago. The heat from this layer rises upward, driving the motion of everything above it. That rising energy fuels transformations that reshape the planet from within. The center of our planet burns with heat that matches and even exceeds the visible surface of the sun. Temperatures in the core reach approximately 5,400 degrees Celsius, hot enough to vaporize any known material if the pressure were not so immense. This extraordinary heat is leftover energy from Earth's violent formation, when countless collisions of planetary material released kinetic energy that melted the young world. Radioactive decay of elements like uranium, thorium, and potassium continues to generate heat even now, billions of years later. The combination keeps the interior molten and active, preventing the planet from becoming geologically dead like Mars or the Moon. This internal furnace drives volcanic eruptions, powers plate tectonics, and sustains the magnetic field that makes life possible. The heat flows outward constantly, moving through the mantle in slow, patient currents. Those currents exert forces strong enough to crack the surface itself. Though the ground feels solid beneath your feet, it floats. The crust rests upon the mantle's slowly flowing rock, rising and sinking according to its weight and density. Where ice sheets once pressed down during ice ages, the land is still rebounding upward now that the weight has lifted. Where sediment accumulates in ocean basins, the crust gradually subsides under the burden. This floating equilibrium, called isostasy, explains why mountains have deep roots extending into the mantle, much like icebergs hidden beneath the sea. The denser oceanic crust sits lower than the lighter continental crust, which is why ocean basins exist at all. As the mantle flows beneath, it carries the rigid plates of crust along with it, creating the slow drift that reshapes continents. The distinction between floating crust and flowing mantle is not always sharp. There are layers between them where properties gradually shift. The continents and ocean floors are made of fundamentally different materials. Continental crust is composed primarily of granite and similar light-colored rocks rich in silicon and aluminum. Oceanic crust, by contrast, is made of basalt, a darker, denser rock rich in iron and magnesium. This difference in density explains why continents stand high while ocean basins sink low. Continental crust can be up to 70 kilometers thick in mountain ranges, while oceanic crust averages only 7 kilometers. The lighter continental material resists subduction, which is why continents are so ancient, some portions dating back more than 4 billion years. Oceanic crust, being denser, readily sinks back into the mantle at subduction zones, making it geologically young, rarely older than 200 million years. This contrast between light and heavy, thick and thin, creates the two-tiered surface of our world. The boundary between these different crusts and the mantle beneath has a name that speaks to the moment of its discovery. In 1909, Croatian seismologist Andrija Mohorovičić noticed something remarkable while studying earthquake waves. He observed that seismic waves suddenly accelerated at a certain depth beneath the surface, indicating a change in material. This boundary between the crust and mantle became known as the Mohorovičić discontinuity, or simply the MOHO. The depth of the MOHO varies, lying about 5 to 10 kilometers beneath ocean floors and 30 to 70 kilometers beneath continents. At this transition, the rock composition changes from the lighter minerals of the crust to the denser peridotite of the mantle. Though no one has ever drilled through the MOHO, Scientists have studied pieces of it brought to the surface by tectonic forces or volcanic eruptions. The discovery of this boundary was crucial to understanding Earth's layered structure. It revealed that our planet is not uniform inside, but organized in shells like a cosmic onion. The behavior of waves at this boundary tells us even more. Earthquake waves are messengers from the deep. As they travel through the planet, they speed up, slow down, bend, and sometimes disappear entirely depending on what they encounter. Primary waves, or P waves, can pass through both solid and liquid, while secondary waves, or S waves, travel only through solid material. By measuring how long these waves take to reach seismometers around the world, scientists can map the interior structure of Earth without ever seeing it directly. The waves move faster through denser, more rigid material and slower through softer or partially molten zones. Sudden changes in wave speed mark boundaries between layers, like the moho, or the boundary between the outer and inner core. Each earthquake becomes an X-ray of the planet's interior, revealing hidden architecture built over billions of years. This method showed scientists how the layers formed in the first place. The story begins with heat, gravity, and the sorting of elements. When Earth was young, it was a molten sphere of rock and metal, heated by the violence of its birth. In that liquid state, gravity performed a great sorting. Heavier elements like iron and nickel sank toward the center, while lighter materials like silicon and aluminum rose toward the surface. This process, called differentiation, created the layered structure we observe today. A dense metallic core surrounded by a rocky mantle and topped with a thin, light crust. The sorting happened over tens of millions of years as the planet slowly cooled. Without differentiation, Earth would be a homogeneous mixture with no magnetic field, no plate tectonics, and likely no life. The process locked away much of the planet's radioactive material in the core, where its decay continues to generate heat. That internal organization created a dynamic world capable of constant change. The uppermost layers of that structure have names that describe their behavior. When geologists speak of tectonic plates, they are not talking only about the crust. The plates that drift across Earth's surface include both the crust and the rigid uppermost portion of the mantle, together called the lithosphere. This layer behaves as a single brittle unit, typically about 100 kilometers thick, though it varies. Beneath the lithosphere lies the asthenosphere, a softer, more pliable zone where rock can flow slowly over time. The contrast between rigid lithosphere and flowing asthenosphere allows plates to move. The lithosphere fractures into pieces along fault lines and plate boundaries, while the asthenosphere deforms without breaking. In essence, the lithosphere rides upon the asthenosphere like sheets of ice floating on water. This arrangement makes plate tectonics possible, enabling continents to drift, mountains to rise, and oceans to open and close. Below the lithosphere, the mantle continues to surprise us with its complexity. Just below the rigid lithosphere lies a zone where rock softens. The asthenosphere extends from about 100 to 700 kilometers deep, where temperatures approach the melting point of mantle rock. Though still technically solid, the material here flows like putty under pressure, deforming over thousands and millions of years. This ductile behavior allows the lithospheric plates above to glide slowly across the planet's surface. Convection currents within the asthenosphere, driven by heat from below, create drag forces that push and pull the plates in various directions. The rock here is so close to its melting point that even small amounts of water or other volatiles can weaken it significantly. Seismic waves slow down when passing through this layer, confirming its softer nature. The asthenosphere is not uniform. It contains hotter and cooler regions, plumes and downwellings, all contributing to the complex dance of tectonic motion. And the deeper you descend, the stranger the conditions become. At the surface, we live under the gentle weight of the atmosphere, about 1 kilogram per square centimetre. But at Earth's centre, the pressure becomes almost unimaginable. The weight of thousands of kilometres of rock above compresses the core to pressures exceeding 3.5 million atmospheres. Under such conditions, matter behaves in ways impossible to replicate in laboratories for more than a fleeting instant. Atoms pack together so tightly that their electron clouds overlap. Iron takes on crystal structures that cannot exist anywhere else. Even the speed of sound changes dramatically at these pressures. This crushing force is what keeps the inner core solid despite temperatures hot enough to melt steel at the surface. Scientists study these extreme conditions using diamond anvil cells and sophisticated computer models, trying to understand how matter behaves when squeezed beyond ordinary limits. The distance between surface and core spans more than just pressure and temperature. To reach the center of the Earth, you would need to journey more than 6,000 kilometers straight down, passing through layers of rock, molten metal, and extreme conditions no human technology could survive. The deepest hole ever drilled, the Kola Superdeep borehole in Russia, reached only about 12 kilometers, barely scratching the crust. The core remains as unreachable as the farthest planets, yet we know its properties through careful observation of how the planet rings and vibrates after earthquakes. Every tremor sends waves through the interior that seismologists can read like musical notes, each frequency revealing something about the composition and state of matter at different depths. The journey downward would take you through distinct realms, each with its own character and behavior. In the zone between upper and lower mantle, minerals undergo transformations unlike anything found elsewhere. Between about 400 and 700 kilometers deep lies a region where minerals transform under pressure into denser crystalline forms. Olivine, common in the upper mantle, becomes wadsleyite, then ringwoodite, structures that pack atoms more efficiently. These transitions happen suddenly at specific depths, creating boundaries that reflect seismic waves. Ringwoodite can hold water within its crystal structure, leading scientists to suspect that vast amounts of water might be locked in this transition zone, possibly more than in all the surface oceans combined. If this hidden reservoir exists, it could play a crucial role in plate tectonics and volcanic activity. At the base of the transition zone, minerals transform again into perovskite and other ultra-dense phases that dominate the lower mantle. These transformations show that even solid rock is never truly static. The restless interior drives motion that eventually reaches the surface, fracturing the lithosphere into pieces that wander the globe. The ground beneath your feet moves, though you will never feel it. Continents drift across Earth's surface at rates of just a few centimeters per year, about as fast as your fingernails lengthen. This pace seems impossibly slow, yet over millions of years it reshapes the entire face of the planet. Maps that seem permanent are only snapshots of a moment in an endless journey. North America and Europe move farther apart each year. India continues pushing into Asia. Africa slowly splits along the East African Rift. The motion is so gradual that no human lifetime can perceive the change. Yet GPS satellites measure it with precision, confirming what the rocks have always whispered. Ancient magnetic patterns locked in stone reveal how continents have wandered, sometimes gathering together, sometimes drifting apart. The present arrangement of land is just one frame in a very long film. In the ocean between the Americas and Europe, this motion is especially clear. Each year, the Atlantic Ocean grows a little wider. Along the mid-Atlantic ridge, molten rock rises from the mantle, cools, and forms new sea floor that pushes the continents on either side farther apart. The process happens continuously, adding new crust while spreading the ocean basin outward at roughly 2.5 centimeters per year. Over the past 200 million years, this slow expansion has transformed a narrow rift valley into a vast ocean. The ridge itself is a wound in the Earth's crust that never heals, constantly fed by magma from below. Submersibles that have explored the ridge have found black smokers, hydrothermal vents, and ecosystems that thrive on chemistry rather than sunlight. The seafloor spreading here is 1/2 of a global system of creation and destruction. While the Atlantic grows, another ocean shrinks. On the opposite side of the world, the Pacific Ocean is slowly but steadily getting smaller. All around its edges, oceanic crust sinks back into the mantle at subduction zones, consumed faster than new crust can form at its mid-ocean ridges. The Ring of Fire, a chain of volcanoes and earthquake zones encircling the Pacific, marks where these plates dive beneath continents and island arcs. Over the next few hundred million years, this process may close the Pacific entirely, bringing the Americas into collision with Asia. The shrinking happens unevenly, with some margins subducting faster than others, creating a complex pattern of mountain building, earthquakes, and volcanic activity. This push and pull between ocean basins is part of a grand cycle that has repeated throughout Earth's history. The last time the continents were all pressed together was not so long ago, geologically speaking. Around 300 million years ago, nearly all of Earth's landmasses gathered into a single enormous supercontinent called Pangaea, meaning all Earth. Surrounded by a global ocean named Pantalassa, Pangaea stretched from pole to pole, its interior harsh and dry, far from the moderating influence of the sea. Fossils of identical species found on continents now separated by oceans prove they were once joined. The shapes of continental shelves fit together like puzzle pieces, showing where they once touched. Climate zones formed long bands across Pangaea, creating deserts in its heart and lush forests along its coasts. For millions of years, this configuration persisted until tectonic forces began pulling it apart, opening the Atlantic and Indian Oceans. The breakup was not sudden, but gradual, taking more than 100 million years, and Pangaea was not the first of its kind. Long before Pangaea, another supercontinent called Rodinia assembled approximately 1 billion years ago. In that ancient world, life was still microscopic, photosynthesis was dominated by bacteria, and the continents themselves were barren rock. Rodinia's configuration remains debated, but evidence suggests it formed when older landmasses collided and sutured together. Mountain ranges rose along its seams, only to erode away over hundreds of millions of years. Around 750 million years ago, Rodinia began to fragment, rifting apart in a breakup that may have triggered one of Earth's most extreme climate events. The opening of new ocean basins changed circulation patterns and atmospheric chemistry. Fragments of Rodinia drifted for hundreds of millions of years before eventually gathering again. This pattern of assembly and dispersal is not random, but follows a rhythm that has shaped the planet for eons. Throughout Earth's history, continents have gathered together and split apart in a repeating pattern known as the supercontinent cycle. Approximately every 300 to 500 million years, the scattered fragments of crust converge into a single massive landmass, only to rift apart again. The cycle is driven by convection in the mantle, which creates upwelling plumes beneath supercontinents that eventually tear them apart. Once separated, the fragments drift until subduction zones consume the intervening oceans and bring the continents back together. Each cycle builds mountains, triggers climate changes, and influences the evolution of life. The formation of supercontinents can lead to mass extinctions, while their breakup often precedes bursts of biological diversification. Geologists have identified at least 6 or 7 supercontinent cycles stretching back more than 3 billion years. Each one left traces in the rock record, patterns of mountain building and erosion that tell of collisions long forgotten. 50 million years ago, India was an island continent drifting northward across the ancient Tethys Ocean. Born from the breakup of the southern supercontinent Gondwana, it travelled thousands of kilometres before colliding with the southern edge of Asia. The impact was slow but unstoppable, crumpling the crust between them and thrusting up the Himalayas, the highest mountain range on Earth. The collision is not over. India continues pushing northward, forcing the Tibetan Plateau upward and triggering earthquakes throughout the region. The rocks of the Himalayas contain fossils of marine creatures, proof that they once lay beneath the sea. This extraordinary journey, from tropical waters to the roof of the world, shows how continents are not fixed but travel vast distances over geological time. The collision altered global climate, affecting monsoon patterns and weathering processes that drew carbon dioxide from the atmosphere. Other seas have also closed and reopened in the dance of continents. The tranquil Mediterranean Sea hides a dramatic history. Around 6 million years ago, tectonic movements closed the Strait of Gibraltar, cutting the Mediterranean off from the Atlantic Ocean. Isolated and trapped in a hot climate, the sea evaporated almost completely in what geologists call the Messinian salinity crisis. For hundreds of thousands of years, the basin was a vast, scorching salt desert, lying more than a kilometre below sea level. Rivers carved deep canyons into the dried seafloor, including a gorge beneath what is now the Nile River. Eventually, tectonic shifts reopened Gibraltar, and Atlantic waters poured back in with catastrophic force, possibly the largest waterfall ever to exist. The refilling may have taken anywhere from months to a few thousand years. Thick layers of salt and gypsum on the Mediterranean floor record this cycle of desiccation and flooding, a reminder that even seas are temporary. Meanwhile, on the eastern edge of Africa, a new ocean is beginning to form. Deep within East Africa, the continent is tearing itself in two. The East African Rift is a massive crack system stretching thousands of kilometers from the Red Sea to Mozambique. Volcanic activity, earthquakes, and dropping valleys mark the places where the crust is being pulled apart. In a few tens of millions of years, the eastern portion of Africa, including parts of Ethiopia, Kenya, and Tanzania, may separate entirely, creating a new ocean basin. The rift's formation is driven by a rising plume of hot mantle material that pushes the lithosphere upward and stretches it until it fractures. Lakes such as Victoria, Tanganyika, and Malawi fill the deepening valleys, early signs of the ocean that will someday flood the region. Standing along the rift's edges, you can see steep escarpments and active volcanoes, witnesses to the slow birth of a new world. This process is happening now, in real time, a visible preview of plate tectonics in action. And far into the future, another supercontinent may be waiting. If the continents continue their current trajectories, they may gather once again into a new supercontinent in 200 to 300 million years. Scientists have proposed several possible configurations. One scenario, called Pangaea Ultima, envisions the Atlantic closing and the Americas colliding with Africa and Europe. Another, Amasia, suggests the continents will converge around the North Pole as the Pacific closes completely. A third possibility, Orica, predicts a more complex assembly involving the reformation of multiple ocean basins. Whichever path the continents take, the result will be a world drastically different from our own, with altered climates, ocean currents, and perhaps entirely new forms of life. The forces that create supercontinents move slowly but inevitably. Long after humanity is gone, the planet will continue its patient work, gathering and scattering landmasses in a rhythm as old as the Earth itself. The engine driving all this motion lies in zones where oceanic crust descends back into the mantle. Not all crust lasts forever. At subduction zones, dense oceanic plates bend downward and sink beneath lighter continental plates or other oceanic plates, descending into the mantle where they eventually melt and become part of the convecting interior once more. These zones form deep ocean trenches, the lowest points on Earth's surface, where the seafloor plunges into darkness. As the sinking slab descends, water trapped in its minerals is released, lowering the melting point of surrounding rock and generating magma that rises to form volcanic arcs. Subduction zones are recycling centers where surface materials return to the deep, completing the grand cycle that keeps Earth geologically active. The Pacific Ring of Fire owes its existence to subduction, as does the Andes mountain range and the islands of Japan. Without subduction, continents would eventually cover the entire planet and tectonics would grind to a halt, but not all plate boundaries involve this downward plunge. At some plate boundaries, neither creation nor destruction occurs. Instead, the plates simply slide past one another horizontally along great fractures called transform faults. These boundaries accommodate the differential motion between plates without producing new crust or consuming old material. The movement is not smooth but occurs in sudden jerks as friction locks the plates together until stress builds to the breaking point. When the plates finally slip, the release of energy produces earthquakes, some of them powerful and destructive. Transform boundaries can extend for hundreds of kilometers, cutting across landscapes and ocean floors in nearly straight lines. They create distinctive landforms such as offset streams, linear valleys, and benches where the ground has shifted over time. The motion is relentless, accumulating meters or even kilometers of displacement over thousands of years. Perhaps the most famous transform boundary runs through California. Slicing through California for more than 1,200 kilometers, the San Andreas Fault marks where the Pacific Plate slides northward past the North American Plate. The two sides move at roughly 5 centimeters per year, though the motion occurs primarily during earthquakes rather than continuously. Over millions of years, this movement has displaced rocks and landforms by hundreds of kilometers. Los Angeles, which sits on the Pacific Plate, is slowly creeping towards San Francisco on the North American Plate, and in about 15 million years the two cities may become neighbors. The fault is not a single crack but a complex zone of fractures, bends and branches that store and release energy unpredictably. Californians live with the knowledge that the ground beneath them is in constant motion, that the next large earthquake is not a question of if, but when. Yet transform boundaries are just one type of plate interaction. Where plates collide head-on, the results are far more dramatic. When two continental plates collide, neither can sink into the mantle because both are too light. Instead, they crumple and fold, thrusting rock upward and creating towering mountain ranges. The Himalayas formed this way when India crashed into Asia, and the process continues today as the mountains rise millimeters higher each year. The Alps, the Urals, and the Appalachians were all born from continental collisions in the distant past. The collision zones produce intense deformation, folding sedimentary layers like fabric and pushing ancient seafloor rocks to elevations where snow never melts. Deep beneath these ranges, the crust thickens dramatically, forming roots that extend down into the mantle, much like icebergs hidden below the waterline. Over time, erosion wears the peaks down, but as long as tectonic forces persist, the mountains continue to rise. In other places, plates move apart rather than together, and creation becomes the dominant process. Where tectonic plates pull apart, a gap opens in the lithosphere and molten rock from the mantle wells upward to fill the void. This process, occurring primarily along mid-ocean ridges, creates new oceanic crust continuously. As the magma cools and solidifies, it forms fresh basaltic rock that slowly spreads outward in both directions, pushing the older crust aside. Divergent boundaries are factories of creation, operating without pause for millions of years. The newly formed crust is hot and elevated, creating underwater mountain ranges that circle the globe for more than 60,000 kilometers. In a few places, such as Iceland and the East African Rift, divergent boundaries rise above sea level, allowing us to witness the birth of new crust directly. Each ridge is a window into the planet's interior, a place where the mantle breathes and the surface renews itself. The mountains formed by convergent boundaries often reach breathtaking heights, and they continue growing even now. High above the clouds, the Himalayas continue to rise. Their growth began around 50 million years ago when the Indian plate collided with the Eurasian plate, crumpling the crust like folded fabric. That collision is still happening, pushing the mountains upward by approximately 5 millimeters each year. The peaks may appear timeless, but their summits climb steadily toward the sky, even as wind and glaciers carve them down. Every tremor in the region, every deep earthquake, is a whisper of that immense pressure still at work. Mount Everest, the highest point on Earth, gains height while simultaneously being worn away by ice and weather. The balance between uplift and erosion determines whether mountains grow or shrink. In the Himalayas, uplift currently wins, though by a slim margin. The region's elevation has profound effects on global climate, affecting monsoon patterns and weathering rates. The rocks lifted high into the mountains carry secrets from a time when they rested far below. At the top of Mount Everest, nearly 9 kilometers above sea level, the rock beneath your feet contains fossils of marine creatures that once lived on the floor of an ancient ocean. The summit is composed primarily of limestone, a sedimentary rock formed from the accumulated shells and skeletons of sea organisms. This limestone formed on the bottom of the Tethys Ocean hundreds of millions of years ago, only to be thrust skyward during the collision of India and Asia. The presence of marine fossils at such extreme elevations is powerful evidence of plate tectonics and the immense forces that shape our world. Climbers at the summit stand atop what was once a seafloor, proof that even the highest places on Earth were once submerged in silent depths. The journey from ocean bottom to mountain peak took tens of millions of years, driven by the slow but unstoppable convergence of continents. These Himalayan peaks are not Earth's longest mountain range, however. Stretching along the entire western edge of South America, the Andes form the longest continental mountain chain on Earth extending more than 7,000 kilometers from Venezuela to the southern tip of Chile. These mountains were built by subduction as the Nazca Plate dives beneath the South American plate, melting at depth and producing volcanoes that pierce the sky. Many peaks exceed 6,000 meters, and some remain active volcanoes, their snowy summits concealing molten hearts. The Andes have risen in pulses over millions of years, with periods of rapid uplift followed by relative calm. Their formation has profoundly influenced climate and biodiversity, creating rain shadows that produce some of the driest deserts on Earth while trapping moisture on their eastern slopes to feed the Amazon rainforest. Ancient civilizations, including the Inca, thrived in these mountains, adapting to thin air and steep terrain, but all mountains, no matter how grand, face an inevitable process that wears them down. Mountains exist in a constant battle between creation and destruction. In young, tectonically active ranges like the Himalayas and Andes, the forces of uplift currently exceed the forces of erosion, causing the mountains to grow taller over time. Rock rises faster than wind, water, and ice can carry it away. But this balance shifts with age. In ancient mountain ranges where tectonic activity has ceased, erosion becomes the dominant force. The Appalachian Mountains of eastern North America were once as tall as the Himalayas, thrust upward by the collision of continents more than 300 million years ago. Since then, they have been worn down to gentle, rounded peaks, their heights reduced by half or more. Erosion is patient but relentless, grinding even the mightiest summits into sand and carrying them to the sea. Every mountain range, given enough time, will return to plains. Some mountains that once rivaled Everest have vanished entirely, leaving only their roots behind. It is hard to imagine now, but the rolling forested peaks of the Appalachians were once a towering range comparable to the Himalayas. They formed during the assembly of the supercontinent Pangaea when the landmass that would become North America collided with Africa and Europe. The collision crumpled the crust and pushed enormous mountains skyward, complete with glaciers, jagged peaks, and year-round snow. For millions of years, they stood as one of Earth's greatest ranges. Then the tectonic forces ceased. The continents began to drift apart, and erosion took over. Rain, rivers, ice, and chemical weathering gradually wore the mountains down, carrying their substance grain by grain to the Atlantic Ocean. What remains today are the ancient roots, exposed cores of once buried rock that tell of a vanished grandeur. The same fate awaits every mountain. Time and weather are forces no summit can resist forever. Sometimes, though, the land can rise even without tectonic forces pushing it upward. During the last ice age, vast ice sheets, thousands of meters thick, covered much of North America and Europe. The immense weight of all that ice pressed the crust downward, deforming the mantle beneath. When the ice melted around 10,000 years ago, the weight lifted, and the crust began slowly springing back, rising like a sponge released after being compressed. This process, called isostatic rebound or post-glacial rebound, continues today. Scandinavia, Canada, and parts of the northern United States are still rising, gaining centimeters of elevation each decade. Ancient shorelines now sit high above the sea, and in some regions, the land rises faster than global sea levels, causing the coastline to migrate outward. The mantle flows slowly back into the space it once occupied, restoring balance to the crust. This gradual uplift will continue for thousands more years until equilibrium is reached. The effect is especially pronounced in Scandinavia. In parts of Sweden and Finland, the land is rising approximately 1 centimeter each year, still recovering from the weight of ice that melted more than 10,000 years ago. Coastal cities have watched their harbours become shallower, and ancient Viking ports now sit inland, stranded above the waterline. The uplift is uneven, greatest in the centre where the ice was thickest and tapering off toward the edges. Tide gauges and GPS measurements track the rise with precision, confirming what ancient maps and archaeological sites have long suggested. In some places, the rebound has exposed new land, extending coastlines and creating islands where none existed before. The phenomenon provides a vivid demonstration of how the solid Earth is not truly solid at all, but flexible over time, responding to changes in load like a slow, viscous fluid. This same flexibility explains why the crust behaves differently in different places. Continents separated by vast oceans sometimes share deep geological connections. If you could rewind time and push North America back against Europe, the Appalachian Mountains would align perfectly with the Caledonian Mountains of Scotland and Scandinavia. They are, in fact, the same mountain range, torn in two when the Atlantic Ocean opened around 200 million years ago. Both ranges formed during the same collision events when ancient continents smashed together to build Pangaea. The rocks on either side of the Atlantic share the same age, composition, and structure, telling an identical story of compression, folding, and uplift. Today, they sit thousands of kilometers apart, separated by a growing ocean, yet they remain geological twins. This connection was one of the key pieces of evidence that convinced scientists of continental drift in the early 20th century. When Alfred Wegener proposed that continents move, many scoffed, but the matching geology across ocean basins became impossible to ignore. Mountains are not the only features built by tectonic forces. The way rock layers deform tells its own story. When tectonic forces compress rock layers, they do not always break. Sometimes they bend, folding into waves and ripples like fabric pushed from both ends. These folds can be gentle or dramatic, ranging from small wrinkles visible in road cuts to enormous arches and troughs stretching for kilometers. Anticlines are upward arching folds, while synclines dip downward. Over millions of years, erosion carves into these structures, sometimes removing the crest of an anticline to expose older rocks at the center, or cutting through a syncline to reveal younger layers. The patterns created by folded rock are among the most beautiful features in geology, visible in mountainsides and canyon walls around the world. They record the immense pressures that shaped them, the slow deformation of solid stone under forces that would seem impossible if we could not see the results. Folding occurs when rock is buried deep enough to become warm and ductile. Nearer the surface, brittle rock fractures instead. Some mountain ranges have been recycled multiple times over Earth's history. The Rocky Mountains of Western North America have a complex history. The range we see today is actually the latest in a series of mountain-building events that have affected the region over hundreds of millions of years. Ancient mountain ranges rose and were worn away completely, leaving only faint traces in the rock record. The current Rockies began forming around 80 million years ago, during an unusual episode of subduction where the oceanic plate descended at a shallow angle far inland, causing compression and uplift hundreds of kilometers from the coast. Since then, the mountains have been shaped by erosion, glaciation, and continued tectonic adjustments. Some peaks are carved from sedimentary rocks that were once flat-lying seafloors, now tilted and thrust skyward. The Rockies are younger than the Appalachians, but older than the Himalayas, caught in that middle stage where uplift and erosion vie for dominance. They remind us that mountain ranges are not eternal. They are phases in a cycle that builds and destroys with patient regularity. And mountains are not the only geological features created by tectonic forces. Volcanoes write their own fiery chapters in Earth's story. Across the planet's surface, roughly 1,500 volcanoes are considered potentially active, meaning they have erupted within the past 10,000 years or show signs of restlessness. Some erupt frequently, others sleep for centuries between outbursts. They exist on every continent except Australia, though many of the most active lie hidden beneath the sea. Each volcano is connected to a magma source deep below, a reservoir of molten rock waiting for the right conditions to break through. These fiery mountains shape landscapes, create new land, and occasionally reshape civilizations. Their locations are not random, but follow patterns that reveal the planet's inner workings. Most cluster along plate boundaries where the crust is fractured and weak, allowing magma to find pathways upward. Volcanic eruptions have always fascinated and terrified humanity in equal measure, and for good reason. They demonstrate that the ground beneath us is thin, that fire still burns just below the surface. The greatest concentration of these volcanoes forms a ring around one particular ocean. Encircling the Pacific Ocean like a necklace of fire, the Ring of Fire hosts 3/4 of the world's active and dormant volcanoes. This horseshoe-shaped zone stretches from New Zealand up through Indonesia, Japan, and the Aleutian Islands, then down the west coasts of North and South America. It marks the edges of the Pacific Plate, where oceanic crust subducts beneath surrounding plates, generating the magma that feeds volcanic eruptions. The Ring of Fire is also home to 90% of Earth's earthquakes, making it the most geologically active region on the planet. Cities and entire nations exist within this zone, their populations living in the shadow of mountains that may awaken at any time. The volcanoes here vary widely in form and behavior, from gently sloping shields to steep explosive cones. Some have been silent for centuries, others erupt almost continuously. Each one is a window into the fiery processes operating in the mantle far below. The shape of a volcano often hints at the nature of the magma beneath it. Not all volcanoes are steep, explosive mountains. Shield volcanoes form when lava with low viscosity erupts effusively, flowing easily across the surface in thin sheets that spread out in all directions. Over countless eruptions, these flows stack upon each other, building broad, gently sloping domes that can stretch for hundreds of kilometers. The Hawaiian Islands are classic examples, built entirely by shield volcanoes whose slopes are so gradual they seem almost flat from a distance. Mauna Loa, the largest shield volcano on Earth, rises more than 9 kilometers from the ocean floor to its summit, yet its slopes average only about 5 degrees. The lava that builds these giants is typically basaltic, hot and fluid, allowing it to travel great distances before cooling. Shield volcanoes tend to erupt less explosively than their steeper cousins, though lava fountains can still shoot hundreds of meters into the air. The eruptions are predictable enough that people sometimes gather to watch them, marveling at the slow, glowing advance of molten rock. Other volcanoes behave very differently. Stratovolcanoes, also called composite volcanoes, tower over landscapes with steep, symmetrical profiles that define our mental image of what a volcano should look like. Mount Fuji, Mount Rainier, and Mount St. Helens are all stratovolcanoes, built from alternating layers of lava flows, volcanic ash, and pyroclastic debris. The magma feeding these volcanoes is more viscous than that of shield volcanoes, often rich in silica, which traps gas and leads to explosive eruptions. Each eruption adds a new layer, gradually constructing a cone that can reach thousands of meters high. The steep slopes result from the thicker lava that does not flow far before solidifying. These volcanoes can remain dormant for decades or centuries, lulling nearby populations into complacency before awakening with devastating force. Their eruptions produce ash clouds that darken skies, pyroclastic flows that race down slopes at hurricane speeds, and lahars, deadly mud flows of volcanic debris and water. The explosive nature of stratovolcanoes is sometimes accompanied by another spectacular phenomenon. During explosive eruptions, volcanic ash plumes can generate lightning storms of extraordinary intensity. As fragments of rock, glass, and crystals collide within the ash cloud, they exchange electrical charge through friction. Lighter particles carry positive charges upward, while heavier ones fall with negative charges, creating a separation that builds until the voltage becomes high enough to spark. The result is lightning that crackles through the dark column of ash, illuminating it from within with jagged bolts. Unlike typical thunderstorm lightning, volcanic lightning can occur at multiple levels within the eruption column and often strikes closer to the ground. Photographs of these events show nature at its most dramatic, fire and electricity dancing together against curtains of ash. The phenomenon helps scientists monitor eruptions, as the frequency and intensity of lightning correlate with the violence of the volcanic activity. Ancient peoples who witnessed such displays must have seen them as the wrath of gods. In truth, they are the inevitable result of chaos, friction, and the planet's raw power made visible. Some eruptions have been so powerful they altered human history. In April of 1815, Mount Tambora in Indonesia erupted with a force unmatched in documented human history. The explosion ejected more than 100 cubic kilometers of rock, ash, and pumice into the atmosphere, darkening skies across the region for days. The eruption column reached more than 40 kilometers high, injecting sulfur dioxide into the stratosphere where it formed aerosols that circled the globe. The following year, 1816, became known as the Year Without a Summer, as global temperatures dropped and crops failed across Europe and North America. Snow fell in June in New England and harvests collapsed, leading to widespread famine. More than 70,000 people died, most from starvation and disease in the aftermath. The caldera left behind is 6 kilometers wide and more than a kilometer deep, now filled by a lake. Tambora's eruption demonstrated that volcanoes can affect climate on a planetary scale, disrupting weather patterns and human societies thousands of kilometers away. But even Tambora pales compared to the volcanic potential hidden beneath a famous national park. Beneath the forests and geysers of Yellowstone National Park lies one of Earth's largest volcanic systems, a supervolcano with a magma chamber estimated to measure tens of kilometers across. This hidden giant has erupted 3 times in the past 2 million years, with the most recent eruption occurring around 640,000 years ago. Each eruption expelled hundreds of cubic kilometers of material, creating calderas that later collapsed and were partially filled by subsequent lava flows. The geological evidence shows that these eruptions would have blanketed much of North America in ash and altered global climate for years. Today, Yellowstone shows signs of continued activity: hot springs, geysers, fumaroles, and ground that rises and falls as magma moves below. Scientists monitor the region closely, though there is no indication that an eruption is imminent. Supervolcano eruptions are rare, occurring perhaps once every 100,000 years somewhere on Earth, but their effects would be catastrophic. The ash, the climate disruption, the collapse of agriculture, all would challenge human civilization. Yet the same volcanic heat that poses such danger also creates the geothermal wonders that draw millions of visitors each year. And volcanic activity, while destructive, also creates some of the most fertile soils on the planet. In the shadow of active volcanoes, life often thrives. Volcanic ash and weathered lava are rich in minerals such as potassium, phosphorus, calcium, and magnesium, all essential nutrients for plant growth. When fresh volcanic material breaks down through weathering, it releases these minerals into the soil, creating some of the most productive agricultural land on Earth. Regions like the slopes of Mount Vesuvius, the Indonesian islands, and parts of Hawaii support dense farming despite their volcanic hazards. The trade-off between risk and reward has drawn people to live near volcanoes for millennia. Rice paddies, vineyards, and coffee plantations flourish where lava once flowed. The soil drains well, yet retains moisture, and its mineral richness can sustain crops for generations. Over time, however, the fertility declines as nutrients are leached away, and new eruptions are needed to refresh the soil. This cycle of destruction and renewal has sustained civilizations, even as it occasionally destroys them. The rocks produced by volcanic eruptions take many strange and wonderful forms. When magma froths with gas and then cools rapidly, it forms pumice, a rock so filled with tiny air pockets that it can float on water. These vesicles, formed by expanding gas bubbles, give pumice its lightweight and abrasive texture. Massive pumice rafts, sometimes kilometers across, have been observed drifting on the ocean after submarine eruptions, gradually dispersing marine organisms to distant shores. Pumice has been used for thousands of years as an abrasive for polishing and smoothing, and in construction for lightweight concrete. But its buoyancy is temporary. Slowly, water seeps into the pores, filling the air spaces, and the rock grows heavier until it eventually sinks. The journey from floating stone to submerged rubble can take days or months depending on the pumice's density. While pumice is the most famous floating rock, certain other highly vesicular volcanic materials can also float briefly, though none are as common or long-lasting. Volcanic rocks exhibit other remarkable properties as well. In moments of explosive eruption or rapid cooling, lava can solidify so quickly that its atoms never arrange into crystalline structures. The result is obsidian, a volcanic glass that gleams with dark beauty and fractures with razor-sharp edges. For thousands of years, humans prized obsidian for tools and weapons, crafting blades sharper than modern surgical steel. The rock is typically black, though iron and other impurities can tint it red, brown, or green, and tiny crystals sometimes create a sheen called rainbow or silver sheen obsidian. When fractured, obsidian breaks with smooth, curved surfaces called conchoidal fractures, leaving edges so fine they can cut at the molecular level. Obsidian is geologically fragile. Over time, water slowly penetrates its surface, causing it to devitrify and lose its glassy nature. Ancient obsidian artifacts often show signs of weathering, their once smooth surfaces becoming dull. Yet, in its fresh form, obsidian is a perfect marriage of fire and instant stillness, a stone caught between liquid and solid. Volcanoes release not just lava and rock, but enormous quantities of gas. When magma rises toward the surface, dissolved gases come out of solution, driving volcanic eruptions with their expanding force. Water vapor is the most abundant, making up more than half of all volcanic emissions. Carbon dioxide follows, along with sulfur dioxide, hydrogen sulfide, and trace amounts of other gases. These emissions can be deadly. Carbon dioxide is heavier than air and can accumulate in low-lying areas, suffocating anyone who enters. Sulfur dioxide reacts with atmospheric moisture to create sulfuric acid, contributing to acid rain and volcanic smog called VOG. The gases released during large eruptions can affect global climate by reflecting sunlight and cooling temperatures for months or years. Over geological time, volcanic outgassing has played a crucial role in creating Earth's atmosphere and oceans, releasing water and carbon from the interior to the surface. Every breath we take contains molecules that once erupted from volcanoes billions of years ago. Most volcanic activity, however, happens where we cannot see it. Hidden beneath the waves, a volcanic system larger than any on land operates continuously. Along mid-ocean ridges, submarine volcanoes erupt in darkness, building new oceanic crust as tectonic plates pull apart. The lava that emerges cools instantly in contact with seawater, forming distinctive pillow-shaped structures. These underwater eruptions lack the explosive drama of terrestrial volcanoes because the immense pressure of the overlying ocean prevents gases from expanding violently. Instead, lava flows quietly across the seafloor, adding new rock to the edges of separating plates. Hydrothermal vents often accompany these ridges, releasing superheated water rich in minerals that precipitate into chimneys and mounds. The process has been building ocean crust for billions of years, creating and recycling the seafloor in an endless cycle. Occasionally, submarine eruptions are powerful enough to breach the surface, giving birth to new islands. Iceland exists because a mid-ocean ridge rises above sea level there, offering a rare glimpse of the process that shapes the hidden majority of Earth's surface. The energy released by volcanic eruptions is nothing compared to what earthquakes can unleash. The ground beneath us is never truly still. Every day, seismometers around the world record thousands of earthquakes, most so faint that only sensitive instruments can detect them. These micro-earthquakes represent the constant adjustment of stresses within the crust as tectonic plates grind past, collide with, or pull away from each other. Faults creep gradually, rocks compress, and pressures build and release in countless small increments. The majority of these tremors register below magnitude 2.0, far too weak for humans to perceive. Yet they are not insignificant. By studying these tiny quakes, scientists can map fault systems, identify areas of stress accumulation, and sometimes predict where larger quakes might occur. The planet hums with this background seismic activity, a quiet conversation of stone and pressure that never ceases. Occasionally, the conversation becomes a shout. When enough stress accumulates along a locked fault, the sudden release produces earthquakes powerful enough to reshape landscapes. The largest quakes on record demonstrate the staggering forces at work in Earth's crust. On May 22, 1960, the most powerful earthquake ever measured struck southern Chile. The Valdivia earthquake registered magnitude 9.5, releasing energy equivalent to thousands of nuclear bombs. The rupture zone extended more than 1,000 kilometers along the subduction zone, where the Nazca Plate dives beneath South America. Ground shaking lasted nearly 10 minutes, toppling buildings, triggering landslides, and permanently altering the landscape. The quake lowered some areas by meters and raised others, redirecting rivers and creating new wetlands. A massive tsunami followed, spreading across the Pacific Ocean and causing destruction in Hawaii, Japan, and the Philippines. More than 5,000 people died, and countless others lost their homes. In the aftermath, entire towns had to be relocated. The 1960 Chile earthquake demonstrated that the planet is capable of releasing energy on a scale that dwarfs human experience. It also provided crucial data that helped scientists understand subduction zones and the mechanics of megathrust earthquakes. The way we measure such events has evolved to capture their true power. Earthquake magnitude is measured logarithmically, meaning each whole number increase represents a dramatic jump in both wave amplitude and energy. When an earthquake increases from magnitude 5.0 to 6.0, the seismic waves recorded on instruments are 10 times larger, but the actual energy released grows by about 32 times. This exponential scaling means that a magnitude 8 earthquake is not twice as powerful as a magnitude 4, but roughly 1 million times more energetic. The Richter scale, developed in the 1930s, has largely been replaced by the moment magnitude scale, which more accurately measures large earthquakes, but the logarithmic principle remains the same. Understanding this scaling helps explain why magnitude 9 earthquakes are so rare and devastating. The amount of stress needed to produce them requires vast rupture zones and extraordinary forces. Most earthquakes fall below magnitude 5, strong enough to feel but causing little damage. The true monsters, those above magnitude 8, occur only a few times per century. Earthquakes transmit energy through the planet in ways that reveal its internal structure. When an earthquake occurs, it generates several types of seismic waves that travel through and across the planet. Primary waves, or P waves, are compression waves that push and pull rock in the direction they travel, much like sound waves through air. They move fastest, racing through both solid rock and liquid at speeds exceeding 5 kilometers per second in the crust, and even faster in the mantle. Secondary waves, or S waves, are shear waves that move rock perpendicular to their direction of travel, like ripples on a rope. They travel more slowly than P waves and cannot pass through liquids because fluids have no rigidity to transmit shear motion. Seismologists use the time difference between P wave and S wave arrivals to calculate the distance to an earthquake's epicenter. This simple principle, applied at multiple stations, allows precise location of quakes anywhere on Earth. The behavior of these waves as they pass through the interior has revealed the planet's layered structure. One key discovery involved S waves and their inability to penetrate certain regions. One of the most important discoveries in seismology came from observing what does not arrive. When a large earthquake occurs, seismometers on the opposite side of the planet detect P waves but no S waves. The S waves vanish because they encounter the liquid outer core and cannot pass through it. This absence creates a shadow zone where S waves are blocked, providing direct evidence that part of Earth's core is molten. The boundary between the mantle and liquid outer core deflects P waves as well, bending them in ways that create additional shadow zones. By carefully mapping these patterns from thousands of earthquakes, scientists have determined the size and properties of the core without ever seeing it directly. The inability of S waves to travel through liquid has also helped identify partially molten zones in the mantle and crust, including magma chambers beneath volcanoes. Seismic waves are geology's most powerful tool for seeing into the unseeable. After a major earthquake, the shaking does not immediately stop. Following a large earthquake, the crust surrounding the rupture zone remains in a state of readjustment. The main shock has redistributed stress along the fault and in nearby areas, and smaller earthquakes, called aftershocks, occur as the crust seeks a new equilibrium. Aftershocks can number in the thousands and continue for years, gradually decreasing in frequency and magnitude. Some are powerful enough to cause additional damage to structures already weakened by the main event. The largest aftershock is typically about 1 magnitude unit smaller than the main shock, though this is not a strict rule. In rare cases, what appears to be an aftershock is actually a foreshock to an even larger event. The 2011 Christchurch earthquake in New Zealand, for instance, was technically an aftershock of a quake that had occurred months earlier, yet it caused far more damage. Aftershocks can be psychologically devastating for survivors, each tremor a reminder of the trauma and a source of fear that the worst might happen again. Understanding aftershock sequences helps emergency responders plan recovery efforts and prepare for continued risk. Not all earthquakes occur near the surface. Most earthquakes originate in the upper crust, within the brittle zone where rocks fracture under stress. But some occur at extraordinary depths, more than 300 kilometers below the surface, within the mantle itself. These deep focus earthquakes are associated with subducting slabs of oceanic lithosphere that descend into the mantle. At such depths, temperatures and pressures should prevent brittle fracture, making these quakes something of a mystery. Scientists believe they occur either through sudden phase transitions in minerals where the crystal structure collapses under stress, or through dehydration reactions that release water and weaken the rock temporarily. Deep focus quakes can be very powerful, sometimes exceeding magnitude 7, yet they cause less surface damage than shallow quakes of similar magnitude because their energy dissipates over the long distance to the surface. They are, however, felt over much wider areas. Studying deep focus earthquakes helps scientists understand the fate of subducting slabs and the conditions within the deep mantle. Some earthquakes are powerful enough to affect the planet as a whole. On March 11, 2011, a magnitude 9.1 earthquake struck off the coast of Japan, rupturing a zone approximately 500 kilometers long. The quake was so powerful that it literally moved the position of Earth's rotational axis by an estimated 10 to 25 centimeters. The redistribution of mass caused by the vertical and horizontal displacement of the sea floor altered the planet's moment of inertia, the same principle that causes a spinning figure skater to rotate faster when pulling their arms inward. The shift also slightly shortened the length of a day by about 1.8 microseconds. While these changes are imperceptible in daily life, they demonstrate the enormous scale of forces involved in great earthquakes. The Tohoku quake also triggered a devastating tsunami that swept across the Pacific, caused a nuclear disaster at Fukushima, and claimed more than 18,000 lives. GPS measurements showed that parts of Japan moved as much as 4 meters eastward in an instant. The event reminded the world that the planet's surface is in constant motion, sometimes gradually, sometimes catastrophically. Occasionally, smaller quakes precede a major event. Before some large earthquakes, a sequence of smaller quakes occurs in the same region, a phenomenon called foreshocks. These may result from the initial cracking of a fault zone as stress reaches critical levels, weakening the rock and allowing partial ruptures before the main break. The challenge is that foreshocks are only identifiable in hindsight. At the time they occur, there is no reliable way to distinguish them from ordinary small earthquakes or aftershocks from previous events. Some major quakes have no foreshocks at all, while clusters of small quakes often dissipate without leading to anything larger. Despite decades of research, earthquake prediction remains elusive. Scientists can identify regions of high risk and estimate probabilities over decades, but pinpointing when a specific earthquake will strike is beyond current capabilities. Foreshocks tantalize with the possibility of warning signs, yet their inconsistency makes them unreliable indicators. The search for predictive patterns continues, driven by the hope that someday we might anticipate these disasters and save lives. Energy from earthquakes travels through the planet in multiple ways. Earthquakes generate two categories of seismic waves: body waves that travel through the planet's interior and surface waves that move along the outer layer. Body waves include the fast-moving P waves and slower S waves, which radiate outward from the focus in all directions. Surface waves, which arrive last, travel only along the crust and include love waves and Rayleigh waves. Love waves shake the ground horizontally, perpendicular to their direction of travel, while Rayleigh waves create a rolling motion similar to ocean swells. Surface waves are typically slower than body waves, but carry more energy and cause more destruction. They produce the swaying, rolling sensation felt during large earthquakes and are responsible for most structural damage. The interaction between these different wave types creates complex patterns of shaking that vary depending on distance, geology, and the earthquake's depth and mechanism. Seismometers record all these waves, creating seismograms that scientists analyze to understand the earthquake's characteristics. The study of how these waves interact with rock has revealed not just the structure of the planet, but also the nature of the materials themselves. Deep below, even solid rock behaves in unexpected ways. If you could grind all the continents into powder and sort them by mineral type, feldspar would dominate. This group of aluminum silicate minerals makes up approximately 60% of the continental crust, forming the foundation of most igneous and many metamorphic rocks. Feldspars come in several varieties, including orthoclase and plagioclase, each with slightly different compositions and colors ranging from white to pink to dark gray. They crystallize from cooling magma and are essential components of granite, the signature rock of continents. Feldspar breaks along two cleavage planes that intersect at nearly right angles, creating blocky fragments. Over time, feldspar weathers into clay minerals, contributing to soil formation. Ancient feldspar crystals in granite can be billions of years old, survivors of countless geological cycles. The abundance of feldspar reflects the light, silica-rich composition of continental crust, so different from the denser, darker basalt that forms the ocean floors. But feldspar is not alone at the top of the mineral abundance list. After feldspar, quartz is the next most common mineral in Earth's continental crust. Composed simply of silicon and oxygen, quartz is extraordinarily hard and resistant to weathering, which is why it persists long after other minerals have broken down. It forms in igneous rocks as one of the last minerals to crystallize from cooling magma, filling spaces between earlier formed crystals. Quartz appears in countless varieties: clear rock crystal, purple amethyst, pink rose quartz, and smoky quartz, among others. It has no cleavage, instead breaking with smooth, curved conchoidal fractures similar to glass. Because of its durability, quartz dominates many sedimentary environments. When granite weathers, feldspar crumbles to clay, but quartz grains remain intact, accumulating as sand that eventually forms sandstone. Beaches, deserts, and river bottoms are often composed primarily of quartz. Its hardness made it valuable for ancient tools before metals were available. Under a microscope, quartz grains from different environments tell stories of their journeys, rounded by rivers or angular from glacial grinding. This simple mineral, two elements bonded in endless repetition, is one of Earth's most enduring substances. Other minerals form under far more extreme conditions. Deep within the mantle, where temperatures exceed 1,000 degrees Celsius and pressures reach more than 50,000 atmospheres, carbon atoms arrange themselves into the hardest natural material on Earth, diamond. These conditions exist only at depths of 150 to 200 kilometers or more, far below the crust in the mantle's upper reaches. There, carbon from subducted oceanic crust, sediments, or primordial mantle slowly crystallizes over immense spans of time. Diamonds are metastable at surface conditions, meaning they should theoretically revert to graphite. But the transformation is so slow that diamonds persist indefinitely once brought upward. They reach the surface through volcanic eruptions that travel at extraordinary speeds, racing upward through narrow pipes of rock called kimberlites before the diamonds can break down. Some diamonds contain mineral inclusions trapped during formation, tiny time capsules that provide scientists with samples of the deep mantle otherwise impossible to obtain. Each diamond is a testament to depth, pressure, and the rare violence required to bring deep earth materials to where we can find them. The time required to form them is nearly incomprehensible. In the deep mantle, time moves on a scale foreign to human experience. A single diamond crystal can take anywhere from 1 to 3 billion years to grow, atom by atom, as carbon slowly accumulates under intense pressure and heat. Some diamonds are older than the oldest rocks on Earth's surface, crystallizing when the planet was young and life had not yet emerged. The growth rate depends on the availability of carbon, the local temperature and pressure conditions, and the presence of fluids that transport carbon atoms to the growing crystal. Most diamonds grow incrementally, with periods of growth separated by millions of years of dormancy. Scientists can sometimes read a diamond's history by studying zones within it that formed at different times or under different conditions. The oldest known diamonds, found in Jack Hills, Australia, date back more than 4 billion years. To hold such a stone is to touch something nearly as old as the Earth itself, formed in darkness and brought to light by volcanic eruption. Yet diamonds are not the only minerals created when ancient seas disappear. When bodies of seawater become isolated from the ocean and evaporate under a hot, dry climate, they leave behind layers of salt. Halite, or rock salt, is simply sodium chloride, the same compound in your kitchen salt shaker, but formed on a geological scale. Ancient evaporate basins contain salt deposits hundreds of meters thick, accumulated over millions of years as seas repeatedly flooded and dried. The Mediterranean's floor holds such deposits from the Messinian salinity crisis. Beneath the Great Plains of North America lie vast salt beds from ancient inland seas. These deposits are economically important, mined for table salt, road salt, and chemical production. Salt also flows under pressure, behaving like a viscous fluid over geological time, forming salt domes that can rise through overlying rock layers and trap oil and gas. The presence of halite in the geological record tells of climates and geographies long vanished, of searing heat and evaporating waters in places now cold or submerged. Some minerals appear metallic but contain no metal at all. Pyrite has deceived countless prospectors with its brassy, metallic shine. Its golden color and weight led hopeful miners to mistake it for gold, earning it the nickname Fool's Gold. But pyrite is iron sulfide, a mineral formed when iron reacts with sulfur in low oxygen environments such as sedimentary rocks or hydrothermal veins. It crystallizes in perfect cubes or 12-sided pyritohedra. Its geometric forms a testament to the orderly arrangement of atoms within. Though not precious, pyrite is not worthless. It has been used as a sulfur source for sulfuric acid production and occasionally as an iron ore. When struck, Pyrite produces sparks, a property that made it useful for starting fires in ancient times. The name comes from the Greek word for fire. Pyrite is common, found in nearly every geological environment, often accompanying actual gold deposits. Its presence can indicate the chemical conditions under which rocks formed. Unlike gold, pyrite tarnishes and weathers, eventually breaking down to form iron oxides and sulfuric acid. Even false gold has its place in Earth's story. Other minerals can grow to astonishing sizes under the right conditions. In the Cave of Crystals beneath the Naka mine in Mexico, gypsum crystals have grown to lengths exceeding 10 meters, some of the largest natural crystals ever discovered. These translucent giants formed over hundreds of thousands of years in a chamber filled with mineral-rich water maintained at a steady temperature near 50 degrees Celsius. The slow, stable conditions allowed calcium sulfate molecules to arrange themselves with perfect precision, molecule by molecule, into colossal selenite beams. The cave remained flooded until miners pumped out the water in the year 2000, revealing a wonderland of crystalline pillars crisscrossing the chamber. The heat and humidity inside make it nearly uninhabitable without cooling suits. The environment is still perfect for crystal growth, but deadly for humans. Gypsum is a soft mineral, easily scratched, and these enormous crystals are fragile despite their size. When the mine eventually closes and flooding resumes, the crystals may continue growing for millennia more. They are monuments to patience, to the slow accumulation of beauty in darkness and heat. Minerals that form in thin sheets have their own unique properties. Mica is unlike most minerals. Its atomic structure consists of layers held together by weak bonds, allowing it to split or cleave into sheets so thin they are flexible and nearly transparent. This perfect basal cleavage makes mica easily recognizable and useful. Muscovite, the most common form, appears silvery or colorless, while biotite is dark brown or black due to iron content. Historically, thin sheets of mica were used as windows before glass became common, and they still serve as insulation in electrical applications due to their resistance to heat and electricity. Mica is a major component of many igneous and metamorphic rocks, including granite and schist. When granite weathers, mica flakes often accumulate, giving certain soils a sparkly appearance. Under a microscope, mica's layered structure reveals itself in cross-section, showing how atomic planes stack like pages in a book. The ability to peel a single crystal into dozens of transparent sheets has fascinated humans for millennia, a reminder that even solid stone has internal structure and hidden properties. Some minerals are among the first to solidify when molten rock cools. When magma cools, minerals do not form all at once. They crystallize in a predictable sequence based on their melting points, a process described by Bowen's reaction series. Olivine, a green silicate mineral rich in magnesium and iron, is among the first to solidify, forming at temperatures exceeding 1000 degrees Celsius. As olivine crystallizes, it removes certain elements from the remaining liquid, changing the magma's composition and allowing other minerals to form next. Olivine is a major component of Earth's mantle and is common in basaltic lavas. Its distinctive olive green color comes from its iron content, though pure magnesium-rich olivine can be nearly colorless. Gem-quality olivine is called peridot, prized for its vibrant green hue. On Earth's surface, olivine weathers rapidly, breaking down to form clays and iron oxides. But in the mantle, where it dominates, olivine is stable and enduring. Some beaches in Hawaii are colored green by olivine sand, eroded from basaltic lava flows. This mineral, so abundant deep below, is a reminder of the fiery origins of the ground we stand on. Other minerals are equally abundant but less often noticed. Calcite, the primary mineral in limestone and marble, has a simple chemical test. Drop dilute acid on it and it fizzes. This reaction occurs because calcite is calcium carbonate, which reacts with acid to release carbon dioxide gas. Geologists in the field carry small bottles of dilute hydrochloric acid specifically to identify calcite in rocks. The test is quick and unmistakable, effervescence confirming the mineral's presence. Calcite forms in a variety of environments, from the shells of marine organisms to cave formations and hydrothermal veins. It exhibits perfect rhombohedral cleavage, breaking into shapes that look like squashed cubes. Some calcite crystals are transparent enough to display double refraction, splitting light into two images when you look through them, a property called birefringence. Calcite is soft, easily scratched by a knife, and dissolves readily in acidic water, which is why caves form in limestone. Over geological time, entire mountain ranges of limestone can dissolve, the solid stone carried away molecule by slightly acidic rainwater. This mineral records the history of ancient seas and the life they once held. Together, minerals assemble into the rocks that form Earth's crust. All rocks begin as one of three types, and igneous rocks are born of fire. When molten material from the mantle or crust cools and solidifies, it becomes igneous rock. If the cooling happens underground, the result is intrusive igneous rock like granite, where slow cooling allows large crystals to form. If magma erupts onto the surface as lava, it cools quickly, forming extrusive igneous rock-like basalt with tiny crystals or a glassy texture. Igneous rocks make up the foundation of continents and the entire ocean floor. They are the primary source from which all other rocks eventually derive. The minerals present, the crystal size and the rock's color reveal where and how quickly it cooled. Some igneous rocks, like pumice, are so full of gas bubbles they float. Others, like obsidian, cooled too quickly for crystals to form at all. Igneous activity renews the crust, bringing fresh material from the depths and resurfacing old, weathered land. Without it, Earth would be a quite dead world like the Moon. These fiery rocks eventually succumb to weathering and become the raw material for another rock type. Sedimentary rocks are born from the debris of older rocks. When wind, water, and ice break down existing rock, the fragments accumulate in layers as sediment. Over millions of years, the weight of overlying material compresses these sediments, squeezing out water and binding grains together through pressure and mineral cements. Sand becomes sandstone, mud becomes shale, and the shells of marine creatures compact into limestone. Sedimentary rocks cover most of Earth's land surface, though they make up only about 5% of the crust's volume. They preserve fossils, ancient footprints, ripple marks from vanished shorelines, and even impressions of raindrops that fell hundreds of millions of years ago. These rocks are history books written in stone, recording past climates, environments, and life forms. Geologists read sedimentary layers like pages, each one representing a specific time and place. The Grand Canyon, with its horizontal bands of sandstone, limestone, and shale, displays nearly 2 billion years of sedimentary history stacked in visible layers. These rocks tell stories that igneous and metamorphic rocks cannot, yet they too can be transformed. Metamorphic rocks are the chameleons of geology, born when existing rocks are altered by heat, pressure, or chemically active fluids without melting completely. The original rock, whether igneous, sedimentary, or even metamorphic, is transformed into something new. Minerals recrystallize, realign, and sometimes react to form entirely different minerals stable under the new conditions. Slate, formed from shale, gains the ability to split into flat sheets. Marble, once limestone, becomes a mosaic of interlocking calcite crystals. Gneiss, transformed from granite or sedimentary rock, develops striking banded patterns. Metamorphism typically occurs deep underground, where temperatures and pressures are intense, often during mountain-building events when continents collide. The degree of metamorphism varies. Slight changes produce low-grade metamorphic rocks, while extreme conditions create high-grade rocks where the original structure is barely recognizable. Metamorphic rocks reveal the forces acting within the crust, the heat of nearby magma, the pressure of overlying mountains, the chemical influence of circulating fluids. They are proof that no rock is permanent, that all can be rewritten given sufficient time and intensity. Together, these three rock types participate in an endless cycle. No rock type is permanent. The rock cycle describes how igneous, sedimentary, and metamorphic rocks transform into one another through geological processes. Igneous rocks once exposed at the surface weather into sediments that lithify into sedimentary rocks. Those sedimentary rocks, if buried deep enough, metamorphose under heat and pressure. If heated further, they may melt entirely, becoming magma that eventually cools into new igneous rock. Alternatively, metamorphic rocks can be uplifted and eroded, their fragments becoming sediment once more. The cycle has no beginning or end, only continuous transformation. A single mineral grain might pass through multiple forms over hundreds of millions of years, from crystal in granite to sand grain to sandstone to metamorphic quartzite and back to sand again. Plate tectonics drives the rock cycle, subducting old crust, generating new magma, building mountains and exposing deep rocks to erosion. Without this movement, the cycle would stall. Each rock you see is just one phase in an endless journey of creation, destruction, and renewal. Some igneous rocks form deep underground, hidden for millennia. Granite is the quintessential continental rock, coarse-grained and light-colored, formed when magma cools slowly deep beneath Earth's surface. The slow cooling allows large crystals of quartz, feldspar, and mica to grow, creating the speckled texture that defines granite. These crystals interlock tightly, making granite strong and durable, which is why it has been used for centuries in construction and monuments. Granite forms the cores of many mountain ranges and underlies much of the continental crust. Over time, erosion strips away the overlying rock, exposing the granite at the surface where we can see and quarry it. Yosemite's iconic cliffs, Mount Rushmore's presidential faces, and countless countertops all showcase granite's beauty and strength. The presence of granite indicates that continents once hosted volcanoes or mountain-building events, though the evidence may now be kilometers below ground or completely eroded away. Granite represents the slow, patient side of igneous activity, rock formed in darkness and secrecy, revealed only when millions of years of overlying material have been worn away. Its counterpart forms in plain sight. Where granite forms in darkness, basalt is born in the open. This dark, fine-grained igneous rock forms when lava erupts onto the surface and cools rapidly, giving crystals little time to grow. Basalt is the most common volcanic rock, covering the ocean floors and forming many volcanic islands. Its dark color comes from iron and magnesium-rich minerals, making it denser than granite. Some basalt flows exhibit columnar jointing, fracturing into hexagonal pillars as the cooling rock contracts, creating dramatic formations like the Giant's Causeway in Ireland. Basalt is the volcanic product of the mantle, relatively unmodified by continental processes. When mid-ocean ridges erupt, they produce basalt. When Hawaii's volcanoes flow, they produce basalt. The rock that forms Earth's oceanic crust is almost entirely basaltic, generated continuously at spreading centers and consumed at subduction zones. Basalt is also found on the Moon and Mars, suggesting it is a fundamental product of planetary volcanic processes. Its simple composition and ubiquity make it one of the most important rocks in understanding how planets work. Other rocks record the remains of ancient life and environments. Walk through a limestone quarry or cave and you are walking through an ancient seafloor. Limestone is composed primarily of calcite, much of it derived from the shells and skeletons of marine organisms. Coral reefs, shellfish, plankton, and countless other creatures extract calcium carbonate from seawater to build their protective structures. When they die, those structures accumulate on the sea floor, layer upon layer, eventually compacting into solid rock. Some limestones are so rich in fossils you can identify individual shells and corals. Others have been recrystallized, their biological origins obscured but still present. Limestone covers vast areas of the continents, evidence that seas once flooded regions now far from any coast. The White Cliffs of Dover, the Pyramids of Giza, and countless caves all owe their existence to billions of tiny marine creatures. Limestone is soluble in slightly acidic water, which is why it forms caves and sinkholes as groundwater dissolves it away. This rock is a collaboration between life and geology, biology turning seawater into stone. Some sedimentary rocks preserve even the most delicate details. Sandstone forms when sand grains are cemented together by minerals precipitating from groundwater. Often, the original textures present when the sand was deposited remain beautifully preserved. Ripple marks from ancient streams, beaches, or deserts appear as delicate ridges frozen in stone. Mud cracks, raindrop impressions, and even the footprints of long-extinct animals can survive, recording moments from hundreds of millions of years ago. These features, called sedimentary structures, allow geologists to reconstruct ancient environments in remarkable detail. Was the sand deposited by wind or water? Were currents fast or slow? Was the climate wet or arid? The answers lie in the patterns locked in sandstone. Some formations preserve entire trackways, showing where dinosaurs walked across ancient mudflats. Others contain fossilized burrows, evidence of creatures that lived beneath the surface. Sandstone is a time capsule, capturing not just the material of the past, but the very shapes and textures of vanished worlds. When buried and subjected to heat and pressure, sandstone transforms into something harder and more enduring. Take limestone, bury it deep, subject it to heat and pressure, and it transforms into marble. The calcite crystals that formed from ancient shells recrystallize into larger, interlocking grains, erasing fossils and original textures. The result is a rock prized for millennia for its beauty and workability. Pure marble is white, but impurities create stunning colors. Iron produces reds and pinks, graphite creates grays and blacks, and serpentine minerals yield greens. Sculptors from Michelangelo to modern artists have chosen marble for its fine grain and the way it interacts with light, seeming to glow from within. Architecturally, marble has adorned temples, palaces, and monuments across civilizations. Geologically, marble reveals the intense forces acting deep within mountain ranges. The Carrara marble of Italy, the Makrana marble of India's Taj Mahal, and the marbles of Greece all began as limestone on ancient sea floors before being cooked and compressed into their current forms. Marble reminds us that beauty often emerges from transformation, that pressure and heat can turn the ordinary into the extraordinary. Another metamorphic rock forms from much humbler origins. Slate begins as shale, a fine-grained sedimentary rock made of compacted mud. When buried and subjected to low-grade metamorphism, the clay minerals in shale recrystallize into tiny mica flakes that align perpendicular to the direction of pressure. This alignment creates planes of weakness, allowing slate to split into smooth, flat sheets perfect for roofing tiles, chalkboards, and paving stones. The transformation from shale to slate is subtle compared to higher-grade metamorphism. The rock becomes harder and more durable, but its overall appearance remains similar, often retaining a dull, fine-grained texture. Slate can be grey, black, green, or purple depending on its mineral content. The ability to split cleanly has made slate economically valuable for centuries. Quarries in Wales, Vermont, and other regions have supplied roofing slate for generations. Geologically, slate represents the first step in metamorphism, a preview of what happens when rocks are subjected to the forces of mountain building. With greater heat and pressure, slate itself transforms into phyllite, then schist, and finally gneiss, each step representing increasing metamorphic intensity. But not all geological change happens deep underground. On Earth's surface, rocks face relentless attack. Physical weathering, also called mechanical weathering, breaks rocks into smaller pieces without altering their chemical composition. Freeze-thaw cycles are particularly effective. Water seeps into cracks, freezes and expands, widening the fractures until chunks break away. In deserts, extreme temperature fluctuations cause rocks to expand and contract, eventually cracking them. Plant roots grow into fissures, prying rock apart with surprising force. Even salt crystals growing in pores can shatter rock from within. Physical weathering increases the surface area of rock, preparing it for chemical weathering and making minerals more accessible to plants and erosion. The process creates everything from boulder fields to fine sand. In mountains, frost wedging breaks cliffs into rubble that accumulates as talus slopes. Along coastlines, waves pound rocks into smooth pebbles and eventually sand. Physical weathering is patient but relentless, dismantling mountains grain by grain. Yet it is not the only force at work. Some weathering transforms rock at the molecular level. While physical weathering breaks rock apart, chemical weathering changes it. Water, oxygen, carbon dioxide, and organic acids react with minerals, transforming them into new compounds. Feldspar, for example, breaks down into clay minerals, releasing dissolved ions that wash away. Limestone dissolves in slightly acidic rainwater, creating caves and sinkholes. Iron-bearing minerals oxidize, rusting like old metal and staining rocks red and brown. These reactions not only weaken rock but also strip nutrients that enter soils and, eventually, the ocean. Chemical weathering is most effective in warm, wet climates where water and heat accelerate reactions. In tropical regions, thick soils develop as rock rapidly breaks down. In cold, dry environments, chemical weathering proceeds slowly and physical processes dominate. The balance between these processes shapes landscapes and determines which minerals persist and which dissolve away. Chemical weathering has even influenced Earth's climate over geological time, consuming atmospheric carbon dioxide and helping regulate global temperatures. Through countless chemical reactions, rock becomes soil, and elements cycle from stone to sea to atmosphere and back. water plays a critical role in one particular weathering process. Water is one of the few substances that expands when it freezes. This unusual property makes it a powerful agent of rock breakdown. When water seeps into cracks and pores in rock and then freezes, it expands by about 9%, exerting tremendous pressure on the surrounding stone. Over repeated freeze-thaw cycles, the cracks widen and lengthen until pieces break away. This process, called frost wedging or ice wedging, is especially effective in climates where temperatures fluctuate above and below freezing. High mountains and polar regions show its effects dramatically. Jagged peaks, rockfalls, and fields of broken stone testify to the power of freezing water. Even in temperate climates, freeze-thaw cycles gradually crumble stone buildings and monuments, requiring constant maintenance. The expansion force is immense, capable of splitting boulders and shattering bedrock. Yet it happens quietly, without drama, water patiently rewriting landscapes one freeze at a time. Living organisms contribute to weathering as well. Plants are surprisingly effective at breaking rock. Seeds germinate in tiny cracks, and as roots grow, they widen those cracks, prying the rock apart with slow, inexorable force. Tree roots can split boulders, buckle sidewalks, and destabilize cliff faces. The process, called root wedging or biological weathering, contributes significantly to rock breakdown, especially in forested regions. Roots also secrete acids that enhance chemical weathering, accelerating the dissolution of minerals. Over time, what begins as a hairline fracture becomes a gaping fissure, and eventually the rock fragments entirely. The iconic image of temple ruins with trees growing through them illustrates this process dramatically. In nature, root wedging works alongside other weathering processes, accelerating the transformation of bedrock into soil. Once rock becomes soil, it can support even more plant life, which in turn continues the weathering process, creating a feedback loop that deepens soil and breaks down more rock. Life and geology collaborate, each shaping the other in an endless partnership. Chemical reactions involving oxygen produce striking visual evidence of weathering. When iron-bearing minerals are exposed to oxygen and water, they rust, just like an old car. This process, called oxidation, transforms iron into iron oxide minerals like hematite and goethite, staining rocks in shades of red, orange, yellow, and brown. The red rocks of the American Southwest, the rust-colored soils of the tropics, and the banded iron formations from billions of years ago all owe their colors to oxidation. These colors indicate that the rocks formed or were exposed in oxygen-rich environments. Early in Earth's history, before photosynthetic organisms produced abundant oxygen, oxidation was rare. The appearance of red beds in the geological record marks the Great Oxidation Event around 2.5 billion years ago, when atmospheric oxygen levels rose dramatically. Oxidation weakens minerals and contributes to rock breakdown, but it also creates beautiful landscapes. The process continues today wherever fresh rock meets air and moisture, slowly painting the planet in warm, earthy tones. Human activity has accelerated oxidation in some environments, particularly where pollution has made rainwater more acidic. Natural rainwater is slightly acidic due to dissolved carbon dioxide, but pollution from burning fossil fuels has made rain in some regions significantly more acidic. This acid rain attacks limestone and marble with particular efficiency, dissolving calcium carbonate and eroding statues, buildings, and natural formations. Historic monuments that stood for centuries have deteriorated noticeably in recent decades due to acid precipitation. The surface of marble becomes rough and pitted, fine details blur, and inscriptions fade. In natural environments, acid rain accelerates cave formation and alters soil chemistry. While some chemical weathering is natural and necessary, the accelerated pace caused by pollution has alarmed conservationists and scientists. Efforts to reduce sulfur dioxide and nitrogen oxide emissions have improved air quality in many regions, slowing the damage. Yet the effects linger in weakened stone and altered ecosystems. Acid rain demonstrates how human activity can amplify geological processes, speeding changes that would normally take millennia and causing impacts that ripple through both natural and cultural heritage. Some rocks develop colourful coatings over immense time spans. In arid environments, many rocks develop a dark, shiny coating called desert varnish or rock varnish. This thin layer, often appearing black or reddish-brown, forms over thousands of years as wind-blown dust settles on rock surfaces and microorganisms help concentrate manganese and iron oxides. The exact formation process remains somewhat mysterious, but the result is unmistakable. Ancient petroglyphs carved into varnished surfaces stand out in stark contrast, the fresh rock beneath lighter than the darkened exterior. Desert varnish requires stable conditions, slow accumulation, and minimal erosion, which is why it forms best in dry climates where rocks remain undisturbed for millennia. The thickness of varnish can sometimes indicate how long a surface has been exposed, making it useful for dating landforms. Aboriginal rock art in Australia, petroglyphs in the American Southwest, and inscriptions in the Middle East all exploit desert varnish, ancient artists recognizing that their work would endure as long as the stones themselves. The varnish is delicate, easily scratched away, but nearly impossible to replicate quickly. Some weathering processes create distinctive rock shapes. In certain granitic landscapes, enormous domes of bare rock rise from the earth, their surfaces smooth and rounded. These features form through exfoliation, a weathering process where outer layers of rock peel away like the skin of an onion. As overlying rock erodes away, the granite beneath expands slightly due to reduced pressure, creating fractures parallel to the surface. These fractures, called joints, allow sheets of rock to separate and eventually spall off. Over thousands of years, layer after layer peels away, creating the characteristic dome shape. Yosemite's half dome and other iconic formations were sculpted this way. Exfoliation is most common in massive, homogeneous rocks like granite, where there are few pre-existing weaknesses to control fracture patterns. The process reveals the fresh rock beneath, which then begins weathering and exfoliating in turn. These domes will eventually wear away entirely, but the process takes millions of years. For now, they stand as monuments to the interplay between pressure, rock structure, and erosion. Understanding the age of rocks requires methods that measure time in ways beyond human experience. To measure geological time, scientists use the natural clocks built into rocks, radioactive elements that decay at predictable rates. Certain isotopes like uranium-238 decay into lead-206 through a series of steps, each with a known half-life. By measuring the ratio of parent isotope to daughter products in a mineral, geologists can calculate how long ago the mineral formed. This technique, called radiometric dating, has revolutionized our understanding of Earth's history. Different isotopes work for different time scales. Carbon-14 is useful for recent materials, while uranium-lead dating can measure ages in billions of years. The precision of these methods has revealed Earth's true age, dated the oldest rocks, timed mass extinctions, and traced the evolution of life. Radiometric dating requires careful analysis to avoid contamination and account for initial conditions, but when applied correctly, it provides absolute ages that transform relative geological time into precise numbers. Every dated rock becomes a fixed point in history, a marker that helps us reconstruct the planet's long story. Different isotopes suit different purposes. Carbon-14 is produced continuously in the atmosphere when cosmic rays strike nitrogen atoms. Living organisms incorporate this radioactive carbon isotope into their tissues, maintaining a constant ratio with stable carbon-12 while alive. When an organism dies, it stops taking in carbon-14, and the existing atoms decay with a half-life of about 5,730 years. By measuring how much carbon-14 remains in organic material, scientists can determine when the organism died. This method is invaluable for archaeology and recent geological events, but carbon-14's relatively short half-life limits its usefulness. After about 50,000 years, so little remains that measurement becomes unreliable. For older materials, different isotopes with longer half-lives must be used. Carbon-14 dating has helped reconstruct recent climate changes, date archaeological sites, and track the timing of extinction events in the late Pleistocene. It has also revealed the age of cave paintings, ancient texts, and even the Shroud of Turin. The method's precision and applicability to organic materials make it one of the most important tools in understanding recent Earth history. For the planet's deeper past, other methods are necessary. For Earth's oldest rocks, uranium-lead dating is the gold standard. Uranium-238 decays to lead-206 with a half-life of about 4.5 billion years, while uranium-235 decays to lead-207 with a half-life of 704 million years. Using both decay series together provides a cross-check that increases accuracy. The mineral zircon is particularly useful because it incorporates uranium into its crystal structure when it forms, but excludes lead, making any lead present clearly the product of radioactive decay. Zircon is also extremely durable, surviving weathering and metamorphism that destroys other minerals. By dating zircon crystals, scientists have determined that Earth is approximately 4.54 billion years old and have identified the oldest known terrestrial materials. Uranium-lead dating has revealed the timing of ancient mountain-building events, volcanic eruptions, and the formation of continents. It works on timescales so vast that human intuition fails, billions of years compressed into laboratory measurements. These ancient dates connect us to a planet unimaginably different from the one we know. The oldest materials ever found on Earth carry ages that predate the planet itself. The oldest known materials on Earth are tiny zircon crystals found in the Jack Hills of Western Australia. These crystals, no larger than grains of sand, have been dated to approximately 4.4 billion years old, formed when Earth was only about 160 million years old. The rocks that originally contained them have long since eroded away, but the zircon survived, eventually becoming incorporated into younger sedimentary rocks. Analysis of these ancient crystals has revealed surprising information. They contain oxygen isotope ratios, suggesting that liquid water existed on Earth's surface when they formed. This pushes back the timeline for oceans and potentially habitable conditions far earlier than once thought. The zircons are windows into an Earth we can barely imagine, a world of volcanic landscapes, a thin crust still solidifying, and an atmosphere nothing like today's. That such tiny fragments survive is remarkable, testament to zircon's durability and the slow processes of geology that can preserve traces of the deepest past. Determining when Earth itself formed required looking beyond terrestrial materials. Earth coalesced from the disk of gas and dust surrounding the young Sun approximately 4.54 billion years ago. This age has been determined by dating meteorites, which are remnants of the solar system's formation and have not been geologically altered like Earth's rocks. The planet formed through the gradual accumulation of planetesimals, bodies ranging from meters to kilometers across that collided and stuck together. The process generated immense heat, melting the young Earth and allowing it to differentiate into layers. Within perhaps 50 to 100 million years, Earth had grown to roughly its current size and had already experienced the giant impact that likely formed the Moon. Since then, the planet has cooled, continents have formed and shifted, and life has emerged and diversified. Knowing Earth's age allows us to understand the pace of geological and biological change, to recognize how ancient the rocks beneath our feet truly are, and to appreciate the vast stretches of time during which the planet has evolved. 4.5 billion years is almost incomprehensible, yet every rock and fossil is a fragment of that story. To organize such immense time, geologists divide Earth's history into named intervals. To make sense of billions of years, geologists have created a hierarchical timescale based on significant changes in the rock record and fossil life. The largest divisions are eons: the Hadean, Archean, Proterozoic, and Phanerozoic. Eons divide into eras, eras into periods, and periods into epochs. Each boundary marks a notable change, such as mass extinctions, the appearance of new life forms, or major geological events. The Phanerozoic eon, meaning visible life, encompasses the last 541 million years when complex, hard-shelled organisms became abundant. It includes the Paleozoic era of ancient life, the Mesozoic era of dinosaurs, and the Cenozoic era of mammals. The timescale is not arbitrary, but based on observable evidence in rocks worldwide, layers that can be correlated across continents by their fossil content and radiometric ages. Learning the timescale is like learning the chapters of Earth's story, each with its own character and significance. We live in the Holocene epoch of the Quaternary period, a tiny sliver at the very end of a vast timeline. Compared to that timeline, humans are extraordinarily recent arrivals. Anatomically modern humans, Homo sapiens, have existed for approximately 300,000 years. Compared to Earth's 4.54 billion year history, that represents just 0.004% of the planet's existence. If Earth's history were compressed into a single 24-hour day, humans would appear in the last second before midnight. All of recorded human history, the rise and fall of civilizations, the construction of pyramids and cities, would occur in the tiniest fraction of that final second. This perspective is humbling. The rocks we study, the mountains we climb, the fossils we uncover, nearly all of them formed long before our species existed. Dinosaurs roamed for over 160 million years, more than 500 times longer than humans have existed. The continents have drifted thousands of kilometers, supercontinents have assembled and broken apart, entire oceans have opened and closed, all without a single human witness. Our species is a newcomer, a brief experiment in a story still unfolding. Yet, in our short time here, we have profoundly affected the planet, leaving marks that future geologists might recognize as a distinct layer in the rock record. Most of Earth's history occurred before complex life even existed. The Precambrian is not a single unit, but a vast expanse of time encompassing 3 eons: the Hadean, Archean, and Proterozoic, collectively representing about 88% of Earth's history. During this immense span, the planet transformed from a molten ball to a world with stable continents, oceans, and an oxygen-rich atmosphere. Early life appeared, likely around 3.8 billion years ago, and for billions of years consisted only of single-celled organisms. Photosynthetic bacteria gradually oxygenated the atmosphere, setting the stage for complex life. Near the end of the Precambrian, the first multicellular organisms emerged, though most left few fossils. The Precambrian rocks are often deeply metamorphosed and eroded, making them difficult to interpret, but they hold crucial information about the planet's early evolution. This enormous stretch of time saw supercontinents form and break apart multiple times, asteroid impacts, volcanic eruptions that reshaped the surface, and the slow chemical transformation of the atmosphere and oceans. Only in its final moments, geologically speaking, did the Earth begin to resemble the world we know. The transition to abundant, visible life marks a crucial boundary. In the early 19th century, geologists noticed that rock layers in different locations contained similar sequences of fossils. Certain species appeared in older rocks, disappeared, and were replaced by others in younger layers. This principle, called fossil succession or faunal succession, allows geologists to correlate rock units across vast distances. A limestone in England and a shale in China might contain the same distinctive fossils, indicating they formed during the same time period, even though they are now separated by thousands of kilometers. This method was crucial for developing the geological timescale before radiometric dating existed. Fossils of trilobites, ammonites, and other extinct organisms serve as markers for specific time intervals. The technique works because evolution is unidirectional. Once a species goes extinct, it never reappears in exactly the same form. By mapping the appearance and disappearance of fossil species, geologists constructed a relative chronology of Earth's history that radiometric dating has since refined with absolute ages. Fossils are not just remnants of ancient life, but tools for reading the planet's history written in stone. Each fossil connects life and geology in the ongoing story of Earth. The names we give to geological periods, Cambrian, Jurassic, Cretaceous, are more than arbitrary labels. Each is defined by a specific section of rock called a type section or stratotype, where the characteristic features of that time interval are displayed. These features include distinctive fossils, unique rock types, and sometimes evidence of major events like volcanic eruptions or mass extinctions. The Cretaceous period, for example, is marked by chalk formations in Europe and ends with a clay layer enriched in iridium from the asteroid impact that killed the dinosaurs. The Carboniferous period is named for the extensive coal deposits formed from swamp forests. By studying these defining layers, geologists learn what Earth was like during each interval, which organisms lived, what climates prevailed, where seas covered the continents. Each period has its own character, its own story preserved in stone. Together they form a continuous record, though with gaps where erosion has removed portions of the narrative. The geological periods are chapters in Earth's autobiography, each one capturing a distinct moment in the planet's long, ever-changing life. The rocks beneath you are memory made solid. Every pebble, every grain of sand carries the trace of time so vast our lives seem like brief sparks against an endless night. Mountains rise and fall, oceans open and close, continents drift like patient travelers across a molten sea. As you rest, Let the weight of deep time quiet your mind. Let your breathing deepen, and let the ancient earth hold you. Sleep well, and good night.